So this presentation is about the exceptions in substitution reactions. So now that you understand what SN1, SN2 reactions are, what are the different factors that affect SN1, SN2 reactions, we will now deal with the exceptions because things are not always clear cut, okay, when you do these kind of reactions. So let's go over again what are the factors that affect SN1, SN2. So it's the nature of the substrate, whether it's primary, secondary, tertiary, the strength of the nucleophile, which remember for SN2, you need to have a good nucleophile, strong nucleophile. For SN1, doesn't matter so much, okay? And then leaving group should be good in both cases. Solvent type will affect what kind of reaction you have, and there are solvents that support reactions and that don't support certain kind of reactions. So we'll talk about that a little bit. So when you're trying to figure out if this reaction is going to happen or not, you look at all of these considerations. Solvent type, not so much, but you do look at all the other considerations and then you decide. Okay, and so in this exceptions, we will still be talking about how these three things will affect whether the reaction is favorable or not. And so when I say favorable, it means is it going to happen or not? Okay, so yes or no. We do have to think about yields, percent yields and reactions. But we're not going to talk so much about it. I will mention it a little bit because technically when you do a reaction, you should get good yield. What's a good yield? Good yield for an organic reaction is anything I would say above 70 to 80%. Anything less than that, you have to think, okay, what happened? Okay, with that. So we're going to talk about the yields also a little bit. So first, let's talk about the substrate. Okay, what are the exceptions? Now, normally for an SN1 or SN2 reaction, you need to have an electrophile that is being attacked by the nucleophile. So nucleophile is negative, right? Electrophile is positive. So when you have a nucleophile that is attacking the electrophile, that is a good reaction to happen. So when does this reaction does not happen? So the reaction will not happen if you have the leaving group on an electron-rich kind of a substrate. So what's an electron-rich? Something like a double bond. So because the double bond is already electron-rich with pi bonds or with pi electrons, then the nucleophile will not like to come to the carbon that is already electron-rich, because remember, nucleophiles likes electrophiles. Electrophiles are electron poor. So these reactions, the two that I have written here, both are not going to work because in both cases, the leaving group is on the electron-rich carbon. Okay, so it doesn't happen. Okay, steric hindrance. So steric hindrance is a lot more critical for SN2 than it is for SN1, as you remember, because in SN2, the nucleophile is coming from behind. Okay, and so in SN1, you form the carbocation, trigonal planar, and so you have no issues. Okay, but in SN2, this is going to be an issue. So here I've given you a substrate, okay, which is looking very sterically hindered, especially when you look at where the chlorine is, which is the leaving group. So the leaving group is actually on a primary carbon. So when you think and if you try to memorize things, and that's why it doesn't work, because you're like, oh, this is a primary halide. If it's a primary halide, it should work like an SN2. But it's not going to work like an SN2 because this carbon is not easily accessible because you have all of these bulky groups over here. Okay, so which means that if you are thinking that this is going to be an SN2 reaction to react with the methoxide, it's not going to happen. So you can still get the product a little bit, but the mechanism is switched now to SN1 mechanism. Okay, the product is still the same. Okay, the product is still the same. Why? Because you have a primary carbocation. Now there is an issue with this reaction, okay, that I'm just giving you a disclaimer for right now. This is not an absolutely true reaction, and I'm just writing this just to show you an example of a sterically hindered electrophile. But otherwise, there are things that can happen to this carbocation, which I'm not doing right now because I'm trying to talk about something else. Okay, and so just bear with me and try to understand what I'm trying to tell you. Okay, which is that this carbon is not easily accessible. So the mechanism is not going to be SN2, it's going to be SN1. If it is an SN1 reaction, you still get the same product. But because this is a primary carbocation, it's not a very stable carbocation. So what does that mean? Your product will not be highly favored, which means your yield is going to be very small, which means if you want to do this reaction, this is not a very good way to do this reaction. Okay, so maybe you want to rethink your synthesis and find something else to do. Okay, because this reaction is not favorable at all. Again, remember my disclaimer. Okay, this intermediate over here, the carbocation, there are some issues, okay, with it. So we'll talk about that later. All right, so then resonance. Okay, this is another issue. So in this case, what happens is that we talked about resonance before, where you can move the carbocation from one carbon to another because you have electrons to move around. Okay, so in this case, what happens is that this is more for an SN1, because in SN2, your carbocation is not being formed, right? In SN2, it's a backside attack. Only in SN1, you are forming a carbocation. So if you're forming a carbocation, then you have to see if there is resonance possible. And how do you know that? So for example, if you look at this kind of a substrate, look at where the chlorine is. The chlorine is on the allyl carbon. Remember the allyl carbon? 1, 2, 3. The third carbon from the double bond is going to be the allyl carbon. So this carbon has a chlorine on it, which is the leaving group. So once it leaves, you get a positive charge over here, which then undergoes resonance, okay, because of the double bond, and it shifts. And then you end up getting this kind of a hybrid where there is delocalization happening. So which means that this is actually quite stable, okay, because if you can form a hybrid, if you can have two resonance structures, then the carbocation is quite stable. So what happens in this case is that you're forming this resonance structure, which once it reacts with the nucleophile, it will give you this product. And then the other resonance structure, in which the carbocation is a primary carbocation, once this reacts with the nucleophile, you end up getting this product. Now, once you look at these two products, you're like, they don't look the same. Okay, and they don't look the same, and that is how we know that there was resonance, okay, in there. So if we did not get two products, if we would just get one product, we know there is no resonance. But because we got two products, we know there was resonance. Why was there resonance? Because of the allyl cation, okay, because of the location of the chlorine. Now, in the previous slide, when I showed you the electron-rich substrate, the electron-rich substrate was when the chlorine was directly on the double bond. In this case, the chlorine is not directly on the double bond, okay? And so please remember, these small differences make a huge difference for us when we are starting to do all these mechanisms. So the bottom here, I've given you another example of resonance structures that you can draw. So just so that you start getting comfortable with resonance, okay? So you'll have to be able to draw 2 to 3 resonance structures. So here, once the chlorine is gone, then you end up getting this carbocation, which once the double bond moves, you end up getting this carbocation, so on and so forth, which if you think about it, and you start reacting each of these intermediates, okay, with nucleophiles, you're going to get 4 products. So that is not a very good reaction, okay? And so if you know that you're going to have an intermediate which can undergo resonance, well, you have to start rethinking your reaction. Do you want those 4 products, okay, to form? And it is going to be resonance stabilized. You can't do anything about this, okay? So similarly here also, you are going to get 2 products. Is that really what you want? Okay, so it's something to be aware of, okay, that when you start doing these kind of reactions, these are the things that can happen. Okay, moving on. So nucleophile now. In this case, we're talking about sterically hindered nucleophile. We talked about the sterically hindered substrate. What was the deal with the sterically hindered substrate? Well, the electrophile has to be accessible, okay? Because if the electrophile is not accessible, and especially in an SN2 reaction, okay, then what are we doing? Okay, because if the carbon is not accessible, then you can't do the reaction. So over here, similarly, this is an SN2 issue. This is not an SN1 issue, okay? So the SN2 has this issue. Now, if you have a primary halide, in case of a primary halide, you have a primary carbon right here, which probably can work with a bulky base. Now, this is T-butoxide. T-butoxide is a huge structure, okay? So if you think about it, it's actually this. So it's pretty big. It looks small when it's written like this, but otherwise it's actually, you know, I mean, so many carbons in there. CH3, CH3, CH3 here. You have a beautiful handwriting, but it's a huge nucleophile. So it has to be able to access this carbon, okay, right here or right here, whichever carbon you're trying to react. In this case, it's a secondary carbon. If it's a secondary carbon and you have such a bulky base, it's not going to happen. Okay, the SN2 reaction, if you're thinking that you want to do here, it's not going to happen. Okay, so you have to be careful. Again, will you get any product at all? Maybe you will, but it may not be in a large quantity. Okay, so you have to be careful about these things and be aware that certain things just don't work. Okay, so try, you know, not to do these kind of things and maybe work on some other kind of reaction. All right, so now let's talk still about nucleophiles, but now we're talking about solvent as a nucleophile. Now, the most important word here for you is going to be solvolysis. Okay, so solvolysis means when the solvent is reacting, okay, with your reaction. So what does that mean for us? It means that your solvent is also your nucleophile. All right, solvent is reacting, it means it's doing something. Generally, solvents are supposed to be just a third party. They're not doing anything. They're just there to support the reaction. They're not supposed to react. But in some cases, they do. All right, so what does that mean for us? When a solvent is reacting, a solvent is supposed to be neutral. So if something is neutral and it is reacting, it means it's not very strong, which means that in this case, you're not dealing with strong nucleophiles. If you're not dealing with strong nucleophiles, then this is only going to be an SN1 problem. It's not going to be an SN2 problem, because in SN2 you need a strong nucleophile. Okay, so this is one thing you're going to have to remember in these cases of exceptions. Is this an SN1 problem or is this an SN2 problem? Okay, because you don't have these problems for both. Okay, in some cases you may have it for both, but here I'm giving you specific things that, okay, this is an SN1 problem. Okay, so in SN1, what is happening? You're forming a carbocation. So once you have the carbocation formed, now the nucleophile can come in. So the nucleophile does not have to be strong. So in which case you can actually use a solvent also to be your nucleophile. Why would you want a solvent to be nucleophile? Well, why not? It's cheap, it's easy. Okay, I don't have to make any kind of a negative nucleophile, which is harder to make sometimes. So I would rather use my solvent, okay, as a nucleophile. So here I've given you two examples, okay, and I want to go through these steps with you so you understand all of these easily. Now you can go on the website and you can find more videos also that I have for you on solvolysis, but I'm going to go through this also with you, okay, one by one with each step. So here you have a tertiary halide, and this tertiary halide, and again remember this is SN1, so I'm dealing only with tertiary halides over here. So with the tertiary halide, here goes the Cl minus, that's the minus, that's the leaving group. So you generate this carbocation. Once the carbocation is formed, then the solvent will attack. Okay, and the solvent, why do I have it coming, why do I have the arrow coming out of oxygen? Because oxygen is the one that has the electrons. Okay, and so the electrons are attacking the carbocation. So then here's what you end up forming. This is the new bond that formed between the carbon and the oxygen. Oxygen still has both of its hydrogens. Now because oxygen now has 3 bonds, it also has a formal charge of +1. So we have to show that there as well. Okay, so don't skimp on all these charges. And then the last step is going to be deprotonation. Okay, so I showed you this mechanism way before when we were learning about SN1. Okay, but hopefully by now you're feeling a little bit more comfortable with reaction mechanisms. Okay, so now what happens? Along comes another water molecule, and that water molecule will deprotonate this oxonium ion. Okay, so this ion over here, this is called oxonium ion. Oxonium meaning that an oxygen with 3 bonds. Okay, so oxonium ion. You're going to come across oxonium ions a lot. All right, so then finally here is your product, the one that I've highlighted in a circle. This is your product that's formed because now you have an alcohol. Okay, so now let's look at another example. It works exactly the same way. Okay, but I really need you to practice this so you understand how these deprotonations work, how the oxonium ion is formed, and things like that. So in this case also you have a tertiary halide, the chloride leaves. So here is the chloride leaving, and then you form a carbocation. So here I took methanol as an example of the solvent and the nucleophile. Again, the oxygen is the one that is doing the attacking. So oxygen is the one that is forming the bond. It is really important for me to that you show also which atom is attaching to which atom, okay? Because if you're not attaching correctly, then what's the point, okay, of forming any kind of structure? You can write anything you want. So make sure that you show exactly what is attaching to what. So carbon is attaching to oxygen. Oxygen still has the hydrogen. Oxygen still has the CH3, right? This oxygen has the hydrogen, it has the CH3. So it still has it, which means that this is the oxonium ion, because oxygen here has the formal charge of +1. Along comes another methanol molecule and it picks up this proton. So now this oxonium ion is happy because now it's getting electrons, and so now it is deprotonated, neutral, and now here we have the ether. So this is the mechanism when you have solvolysis. So again, when does solvolysis happen? It happens only for SN1. Why? Because in case of solvolysis, the nucleophile is weak. It's not a good nucleophile, so solvolysis happens only in SN1. Okay, now these are very common mechanisms. Okay, so you should practice them even on your own, and you can just close your eyes right now and just write this over again so you understand how to do all these things. Now the solvents that will react most of the time when you're doing solvolysis is going to be water and alcohols. You will not find any other solvents that we work with that will react, okay, over here. So it's generally water and alcohols. That's what's reacting here. Now, the third thing is about leaving group. Okay, so you talked about substrate, you talked about nucleophiles. All right, now we're talking about leaving group. Now, leaving groups in general are supposed to be good leaving groups, okay, which means that regardless of whether you have an SN1 or an SN2 reaction, your leaving group has to be good, because if it doesn't leave, or if it is a strong base and it doesn't want to leave, it's not stable, then what's the whole point of doing a reaction, okay? So in some cases, like, you want to do the reaction with the particular starting material you have because you don't have money to buy any other chemicals. So you're like, I need to do it with this. This is the only thing I have in my lab. Okay, so I have to do this. So in those cases, what you do is you try to manipulate the reaction. Okay, so one of the things that I've written out over here for you that you can see is that if you start with an alcohol and you want to do this kind of a substitution of an alcohol with the bromide, it's not going to happen. Why is it not going to happen? Because your leaving group here is hydroxide. Hydroxide is way stronger of a base than bromide. So this reaction is not favored at all, okay, because the leaving group is way stronger base than the nucleophile. So it's not favored, okay, so you're like, I still want to do this reaction. So what you do then is you take the alcohol and you protonate it, okay, using an acid. What kind of an acid? HCl, sulfuric acid, phosphoric acid. So not so much HCl, maybe phosphoric acid, a weak acid is okay, dilute sulfuric acid is okay. So you take any kind of an acid, a mineral acid, and you protonate this alcohol. So what does protonation mean? Is that now this is the acid, so which means this is the base, and the base here is the oxygen, because oxygen has the electrons. So that picks up a proton here. Once it picks up a proton, now it's protonated. So again, you can see the oxonium ion here. And now in this case, the oxonium ion, if you look at it carefully, sorry about this, this is a hydrogen here at the back. So when you look at that, okay, just what we have here, this is water. Okay, so which means that if you have water, that's the leaving group. And water is a fantastic leaving group. Okay, so compared to OH minus and water, because now remember, actually bromide, I shouldn't say water, because here, let me write this again. So compared to bromide, okay, so water and bromide, because bromide is your nucleophile and water is the leaving group over here. So bromide is definitely going to be a better nucleophile than water, because bromide is negatively charged. So because it is negatively charged, it's a better nucleophile. So now that you have converted the OH into a good leaving group by protonating it, now you can actually go ahead and do the substitution reaction. So now you can do an SN2 reaction and it's going to work just fine. Okay, you can do SN1 reactions also like this. Okay, so here you can convert an alcohol into a good leaving group. So regardless of whether it's an SN1 or SN2, it doesn't matter. This is going to work. Okay, so protonation of alcohols is like the easiest things to do. Okay, there are some issues with protonation, and we will talk about that. The other way, or in the problem to kind of get rid of those problems, you can also make alcohols into tosylates and mesylates, which we are going to do when we get to alcohols a little bit more. And in some textbooks, they actually cover tosylates and mesylates even in SN1, SN2 reactions, because they do turn the alcohol groups into good leaving groups. Alcohol groups, OH groups, are not really very good leaving groups because hydroxides are very strong bases, so they're not very good leaving groups. So in any case, so this is how to make a bad leaving group into a good leaving group. Okay, so let's go on to the next thing. Rearrangement. Okay, so rearrangement is a category on its own. All right, it's nothing to do with the leaving group or anything like that, but rearrangement is a category on its own, and it happens primarily for SN1 reactions. Okay, so it's kind of a substrate category. I could probably put it there in the substrates, but we'll just deal with it separately. Okay, because this is something you're going to have to learn and deal with from now until whenever. Okay, so SN1 reactions is the only place where this happens. Okay, why so? Because there is a carbocation formation. So you're thinking, okay, so what? Big deal, okay, that you're forming a carbocation. Well, carbocations have different stabilities. All right, so you know that the tertiary is more stable than secondary, which is more stable than primary. So what happens then is when you form a carbocation in certain reactions, the rearrangement occurs because the compound or the intermediate that you form can rearrange to form a better, more stable carbocation. There's nothing you can do about it. It's going to happen. Okay, so you have to be careful and say, okay, is rearrangement going to happen in this case or not? Okay, so what happens in this case then? So once the rearrangement happens, you end up changing the carbon skeleton, which means that you don't have what you started with. Let's see an example. So let's look at this structure over here. So here is your substrate and here is the leaving group, okay, that you have, the chlorine. So chlorine leaves, fine. You want to have an hydroxide over here. You want to do an SN2 reaction, hydroxide, pretty small nucleophile. You can do an SN2 over here. So this is what you are hoping to make when you go into the lab. So you're like, yay, I got everything done and I'm going to do this. It turns out you don't get this product, okay? And that's because you forgot about rearrangement. So what happens? Let's see the mechanism. The chlorine leaves, as usual, that's your leaving group. And why does it leave? Now, secondary carbocations are okay. I mean, stability-wise, they're in the mid form, all right? Primary carbocations are not going to form, okay? It's very, very rare that you're going to form a carbocation that's primary. Secondary, you can form, all right? And this one, don't forget, it's not that super sterically hindered, but it's a little bit sterically hindered. So which means that, okay, SN1 is probably going to happen over here. So then you have the Cl minus leaving, which means you form a carbocation. So what is the rearrangement that is happening here? Okay, and the rearrangement that is happening here is that this hydride is shifting to this carbocation. So once the hydrogen shifts over here, this carbocation now will shift over here. How does it shift? It doesn't shift. The hydride has shifted and the hydrogen took its electrons with it. So now there are no electrons on this carbon. Okay, I want you to think about this properly. All right, don't think of it as a carbocation shift. Think of it as a hydride shift. Okay, that's a much better way of learning this, because if you say there's a carbocation shift, that's absolutely wrong, because carbocation cannot shift. It does not have electrons, okay, to shift. A carbocation will result in shifting because of a hydride shift. Okay, so it's much better to say that you're actually doing an H shift or a hydride shift in order to form this. Now, don't just write an H shift, okay? You got to show this also. So let me write this again for you so you can see that this is what you need to show in order to show that hydride shift happening. So once that hydride has shifted, once the hydrogen has shifted, and again, H shift is actually hydride, which means it's taking its electrons with it. If it takes its electrons with it, now this carbon has no electrons on it. So that's where the carbocation now forms. Now this carbocation is a tertiary carbocation. This one was a secondary carbocation. Tertiary, more stable than secondary. So that's why this rearrangement happened. Okay, so now you can have the hydroxide come in and attack this carbon, and this is the product you get. So now you can look at the, the product that you were thinking you will get versus the product that you actually get, and you're like, oops, I completely forgot about rearrangement. Okay, so one of the things that you have to do when you're doing SN1 reactions is that you have to look at your starting material and say, am I going to have rearrangement in there? So you have to take a second and take a break and just, look at that peacefully. Okay, so a few more things about rearrangements before we can move on is what can you shift? Okay, because you can't shift everything, all right? So there are only 3 groups that you shift. It's going to be a hydride, a methyl group, and a phenyl group. Okay, you cannot move any other group. Okay, so please remember, just these 3 groups you can move. A hydride, a CH3, which is a methyl group. So there's a methyl shift and there's a phenyl shift. Hydride, methyl, phenyl shifts. That's it. Okay, those are the only groups that are possible to move. You can only move things one time. Okay, it's not like you keep shifting until you get something more stable. You can't do that. One time, that's it. The shift occurs only to form a more stable ion. Now, if you were thinking, oh, I can go ahead and do a shift, where this is shifting, to hydrogen is shifting over here. Well, there is no difference between these two. So this is secondary and this is secondary. So what's the reason for shifting? Okay, there is no reason for shifting. So you have to make sure that you're going towards a more stable carbocation in order to do the shift. How do you predict, okay, that there's going to be a rearrangement? First of all, see if there's a mechanism is SN1. If it's SN2, there is no rearrangement, okay? So you don't have to worry about anything. So if it's SN1, how can it be SN1? SN1 would be if it's solvolysis, okay, or you have a secondary halide, okay, or you have a weak nucleophile in there. So, or maybe the products are given to you, and when you look at the products, you're like, oh my God, they look nothing like the starting material. Something has changed. Okay, so you know that rearrangement has occurred. So any of these things will give you a clue. Okay, so once you know it is an SN1, the first thing you have to do is you have to form a carbocation. Okay, because if you don't form the carbocation, how are you going to visualize what is going to shift? Okay, and then you start shifting, okay, whatever you can shift, all right, from here. Okay, so let's look at some examples and see if you want to shift anything, all right. So in the first one here, the Cl is leaving, okay, so that's minus Cl minus over here. So once you form this carbocation, can you see any shifting happening? Yes, I hope you can. So this methyl group, if it shifts over here, then this carbon is going to form the carbocation. Okay, so I'm just going to write it over here carefully. So this methyl group is shifted to the second one here. And now this carbon right here, 1, 2, 3. So 1, 2, 3 carbon, this still has a methyl group. So this still has a methyl group here. And now it will get the carbocation. Okay, so that's the one that is going to be formed from the first one. So yes, there will be a shift in this one. What about the second one? So here the Cl minus is going away. So again, that's gone. So here in this case, you form this carbocation. And now what happens is that you're going to have a hydride shift. Okay, so I think this should be a hydrogen over here. So now that you get a hydride shift over here, now your carbocation is going to move. It's not going to be in the same place anymore. So this is where you get it. How do you decide whether to move the carbon or the hydrogen? Well, if you move the carbon, you get the same thing. Okay, so let me show you that if you move the carbon, if you say, okay, I want to move this carbon, well, sure, you can move the carbon, but then your vacancy for the electrons is on this carbon. So what's the difference between this and this? Both of these are secondary carbocations, so there's no need to shift. So in these cases, you have to move the hydrogen. Hydrogen sometimes a little bit harder to shift because hydrogens are invisible. You don't see them. So you really have to make a conscious effort and say, oh, I have to move a hydrogen, okay, in order to form a stable carbocation. All right. Okay, the last one now here, once the Cl leaves, you get a primary carbocation over here. So what are you going to shift over here? You can actually shift this if you wanted to. Now, does this happen? So this is a really dicey one, okay, because I'm forming a primary carbocation, which I told you does not form, okay? So there is a thing called hyperconjugation, okay? And in some cases, what happens is, depending on what kind of reaction you're doing, this step where the chlorine is leaving and where the hydrogen is shifting almost happens at the same time. So that means you end up with a carbocation like this automatically. You never form the primary carbocation. Okay, so the two things happen at the same time. So because you're not supposed to form a primary carbocation, all right? So you automatically go ahead and do the hydrogen shift or hydride shift. Please remember, you cannot move anymore, okay? Just one time is enough, because I'm sure you're thinking, oh, if I move once more, I can get a tertiary carbocation, but you know what? You can't move on anymore. Just one time is enough, okay? So that is how you would decide whether any rearrangement is going to occur or not for any intermediate. So this slide you have seen before also. Again, the only thing I would like to add for the SN1, SN2 is the rearrangement. So in SN2, there is no rearrangement. SN1, there is a rearrangement. Okay, that happens, which is, it can be a good thing and it can be problematic also, okay, in some cases. And again, here are your keywords and concepts again. So there's nothing new over here. Everything is still the old stuff. So just in case you want to review, it's all here.